My project has studied the congestion control algorithm of TCP Westwood and Westwood Plus based on bandwidth estimation. By using X reception rate to estimate the available bandwidth, TCP Westwood selects a slow start threshold and a congestion window consistent with the estimated bandwidth. The mechanism of TCP Westwood is termed as faster recovery and is particularly effective over wireless links where sporadic losses are often misinterpreted as congestion losses. TCP Westwood Plus functions well in the presence of Ierg compression. It relies on bandwidth samples collected every round-trip time. However, both of them do not take the CV limit case and application limit case into account. Besides, the current proposed method, act count, actually overshoots the estimation. Therefore, in this project, several modifications are come up with to improve the bandwidth estimation accuracy. First, let me introduce TCP Westwood. It is a TCP variant with center-side bandwidth estimation and modification of congestion window. TCP Westwood exploits TCP acknowledgement packets to estimate the bandwidth, and it continuously estimates bandwidth by monitoring the Ierg reception rate at the center side. If an Ierg received at time t, a corresponding amount of data dk has been transmitted over the channel and received by the TCP receiver. Therefore, the sample of connection bandwidth is bk equal to dk over tk. The samples are filtered by discrete time loss path filter. When dupe X are received, the sender sets the congestion window to be current bandwidth estimation times the minimum of detected RTT. TCP Westwood Plus is the improved version of TCP Westwood. It differs from Westwood that it works properly in presence of Ierg compression. The sender counts the amount of data decay during the last RTT-TK and then computes a bandwidth estimation sample as bk equal to dk over tk. And then it also filtered by an exponential filter. Considering the effects of delay and cumulative X, a procedure called act count is provided to remove disruptions. The meaning of C-wind limited is that after sending out packets, the congestion window is exhausted and no more packets will be sent until an Ierg returns at the sender. Consequently, during that RTT, there will be an idle period. C-wind limit case will cause underestimation since the denominator tk is larger than expected. In this figure, it plots out the inter-arrival time between two packets, and these outliers are actually the C-wind limit time. As for application limit case, it differs from C-wind limit case that the sender now becomes idle simply because it stops transmission, which means that even if the congestion window is not exhausted, no packet will be sent out. Similarly, there will also be an idle period that should not be considered when doing the bandwidth estimation. When troubleshooting the Westwood using simulation tool, overestimations are observed if low-pass filter is removed. The reason is found in the act count method dealing with delayed and cumulative acts, and it caused by the over-calculated numerator decay. In the new bandwidth estimation algorithm, a key variable called last receive time is introduced to keep track of the time when the sender receives the last Ierg before estimating the bandwidth. Thus, the new bandwidth estimation equation is as the following, where tk is the exact time when the sender calculates the bandwidth estimation for the case RTT, and tr is the timestamp of the last received Ierg during the RTT, which is equal to the last received time. Also, after we found out the bug in the new act count procedure, we changed the relationship, and it shows in the later result that it can solve the overestimation problem. As for results, we use two topologies to run simulation. The first one is one flow topology. It includes one sender and one receiver, and two competing flows topology includes two senders and one receiver, and they will share the bottleneck bandwidth. The network parameters are as following. Under the same conditions, one Westwood flow is simulated, and then one Westwood M is simulated. Trace data are also used for simulation. The cyan curve is the actual bandwidth that varies from time to time. And the blue curve is estimated by the new algorithm, and it is one RTT shifted since the estimation is one RTT later. Besides, simulation with random loss in the channel are also conducted. The random loss rate is 0.001. Overall, Westwood M performs better than Westwood in this case. The next results showcase application limit case. In NS2, one flow can be stopped and then resumed after a while. As for the simulation, the flow stopped at 2 seconds and then resumed at 3.5 seconds. The algorithm can successfully detect the application limit period and estimate the bandwidth accordingly. The results are as following. Two flows will share the 10 megabit bandwidth, which means that fair share bandwidth will be 5 megabit for each flow. For the first figure, two Westwood M flows compete with each other, and this figure shows the fair share result. With random loss rate in the bottleneck bandwidth, the loss rate is equal to 0.01. Westwood M will actually outperform Westwood and Cubic. That's all.